conclusion of the preceding lesson was that we need a tool to optimize our combinational circuits. This tool is Boolean Algebra and is the topic of this lesson. A Boolean Algebra, B, is a set over which two operations called Boolean sum and Boolean product are defined and satisfy 5 postulates. A first postulate is that the Boolean sum and product are internal operations. That means that if A and B are in B, then their sum and their product are also in B. It's what we meant when we said that there are operations over the set B. A second rule is that to each operation corresponds a neutral element. That means that given an element of B, there exists an element 0, always the same element, such that A plus 0 is equal to A. And there exists within B an element 1, such that A times 1 is equal to A. The next rule is that to each element corresponds also an inverse element. That is to say, given any element A of B, there exists an inverse of A bar, or not A, such that A plus not A is equal to 1 and A times not A is equal to 0. Next rule, both operations are commutative. That is to say that A plus B is equal to B plus A and A times B is equal to B times A. And finally, rule number 5, both operations are distributive, not only as in the case of the real number, that is to say A times B plus C is the same as A times B plus A times C, but also in a symmetric way, the sum is distributive with respect to the product. A plus B times C is the same as A plus B times A plus C. As a matter of fact, all rules are symmetric in a Boolean algebra. Given some rule, if you interchange sum and product, 0 and 1, you get another rule. A first example of Boolean algebra is the set 0, 1, with the operations defined in this table. The product A times B is equal to 1 when A and B are equal to 1. It's the so-called AND function whose implementation is a 2-input AND gate. The sum, the Boolean sum A plus B, is equal to 1 if A or B or both are equal to 1. It is the so-called OR function, and its implementation is a 2-input OR gate, and OR. Finally, the unary operation inversion is defined as follows. If A is 0, not A is 1, and if A is 1, not A is 0. And its implementation is an inverter. Then, with this definition of the operations, you could check that the 5 postulates are satisfied. For example, let us check the distributivity of the product with respect to the sum. For that, we can consider all the combinations of values of A, B, and C, and compute for each combination the value of both members of this equality. Let us compute first B plus C. B plus C is equal to 1 if B or C are equal to 1, so that B plus C is equal to 1 here, here, here. In this case, it's equal to 0, 1, 1, 1. Then we multiply B plus C by A. A is equal to 0 in the first 4 rows and to 1 in the other rows. Thus, A times B plus C is equal to 0 in the first rows, and it's equal to B plus C in the other rows. Let us compute now A times B. A times B is equal to 1 if and only 1 both A and B are equal to 1. So A times B is equal to 1 in this row and in this row. The computation of A by C consists of looking in which rows A and C are equal to 1, that is to say here 1, 1, and here 1, 1. Then we compute the sum of A times B and A times C. The sum is equal to 1 if A times B or E times C is equal to 1. That is to say, in this row, and this row. And finally, it's only a matter of comparing both functions and to check that they are equal. An important comment from the property from this property is that this circuit that implements this expression and this other circuit that implements the other expression are equivalent. Equivalent, I mean that they implement the same Boolean function. And obviously, the second circuit is better than the first, than the other one, because it includes less logic gates. So there is a relation between all those properties and rules and the complexity, the cost of the corresponding circuits. We have seen a first example of Boolean function, of Boolean algebra. The set 0, 1 is a Boolean algebra, but more generally, the set of n-variable switching functions, functions that are defined by an application, a mapping from the set of all n components binary vector to the set 0, 1. This set of switching functions is also a Boolean algebra. Given two switching functions, let us say f and g, then we can define f plus g, f times g, not f, in the following way. We say that function f plus g, for example, at point x0, x1, and so on, is equal to the value of f at this point plus the value of g at this same point. The same in order to define the product of f by g, and the same in order to define the complement or the inverse of f. The neutral elements of this algebra are the constant functions 0 and 1. Now, apart from the postulates, there are several properties that can be demonstrated and used to minimize combinational circuits. The first one says that the inverse or the complement of 0 is 1 and the inverse of 1 is 0. It is obvious as 0 plus 1 is 1 and 0 times 1 is equal to 0. A second property is idempotency of the operations. That means that adding a to a, you get a, and multiplying a by a, you get the same value a. We could try to demonstrate the idempotency of the Boolean sum using the postulate as an exercise. We know that a is the same as a plus 0. It's postulate number 2. 0 can be replaced by a times not a. It's postulate number 3. Then we use the distributivity law and substitute a plus a times not a by a plus a times a plus not a. But we know that a plus not a is equal to 1, so we get this new expression. And we know that a plus a times 1 is the same as a plus a. So we have demonstrated that a is equal to a plus a, idempotency of the sum. As an exercise, you could try to demonstrate the other idempotency rule, that is a times a equal to a. Actually, if you take the demonstration of the idempotency of the sum and just interchange sums and products and 0 and 1, you get the demonstration of the other idempotency law. Let us continue with the useful properties. Involution means that inverting twice an element, you get the same element. Associativity is the same concept as in the case of the integer or the real number. You can check this property in the case of the two-element Boolean algebra, for example, with a table, as we did before, including all the value combination of a, b, and c, and check that a plus b plus c is the same as a plus b plus c, and the same with the Boolean product. Absorption law is very useful to minimize Boolean expression. It states that a plus a times b is equal to a. You could say that a absorbs the product a times b, and symmetrically a times a plus b is equal to a. In this case, you could say that a absorbs the sum of a and b. Another interesting property that can use to minimize expression is that a plus not a times b is the same as a plus b, or symmetrically that a times not a plus b is the same as a times b. As an exercise, let us try to demonstrate this property. A plus not a times b could be replaced by a plus ab, absorption law, plus a times b. But a times b plus ab is the same as a plus not a times b. This is 1, so that finally this is equal to a plus b. Finally, the Morgan laws say that the inverse or the complement of a sum is equal to the product of the inverses, and symmetrically that the inverse of a product is the sum of the inverses. and this law can be generalized to any number of sum terms and product factors. Now, a little quiz. In this third section, we are going to focus on the relation between Boolean expressions, truth tables, and combinational circuits implemented with logic gates. First point, given a Boolean expression, for example, this one, we can define an equivalent table that we can generate as follows. Consider all the combination of value of A, B, and C, and successively compute not C, B times not C, not A times B, finally the sum of B times not C and not A times B, so that finally you get this function. Conversely, given a truth table, can you generate an equivalent expression? The answer is yes, and for that we introduced first the concept of literal. A literal is a variable or an inverted variable. Another concept is that of n variable minterm, a product of n literals such that each variable appears only once is a minterm. Here is an example. If n is equal to 3, there are 8 minterms, those ones. You can see that in every expression there are 3 literals and they are all different. Then, given a minterm, we can see that there is one and only one set of variable values such that this minterm is equal to 1. Assume that n is equal to 3 as before, and consider here the 8 combinations of values of 3 variables A, B, and C, so that you can define 8 minterms and observe that the first one, this one, not A times not B times not C, is equal to 1 if and only one ABC is equal to 0, 0, 0. The second one is equal to 1 if and only if ABC is equal to 0, 0, 1, and so on. So to each minterm, and we will call them M0, M1, so on up to M7, corresponds one value combination of A, B, and C, such that the corresponding minterm is equal to 1. Question: how can we generate an expression from a table? A straightforward method is to look for the ones of the function and associate with those ones the corresponding minterm. In this case, in this example, function f has 3 ones. To those 3 ones correspond those minterms. Minterms not A times B times not C. Actually, effectively, this product is equal to 1 if A is equal to 0, B equal to 1, and C equal to 0. To this one correspond to this product, not A times B times C, and to this one correspond the product A times B times not C, so that we can express f under this form, under the form of the sum of 3 minterms, minterm M2, M3, and M6, that is to say, under the form of this Boolean expression. Actually, this is very like what we did before when we said something like that f is equal to 1 if, and then we write the following conditions: ABC is equal to 0, 1, 0, or ABC is equal to 0, 1, 1, or ABC is equal to 1, 1, 0. We could say that we have formalized in an algebraic way this kind of condition. By the way, this type of representation as a sum of minterms is called canonical representation of the function. To summarize, assume that we have specified a combinational circuit by means of some functional description. For example, this very simple piece of program. This description can be translated to a table by considering all the value combinations of A, B, and C, and executing for each of those combinations this piece of algorithm. Then, from the table, you can generate the corresponding canonical expression with as many minterms as ones of the function, in this case 3 ones, to which correspond 3 minterms. Then, using the rules and properties of the Boolean algebras, you can simplify the expression. In this case, for example, you can see that here you have not A, B, not C, and here not A, B, C, that can be replaced by not A, B times not C plus C, which is equal to 1, so that finally you get this term, and the same for the other one, so that finally you get a simpler expression to which you can associate a circuit made up of AND gates and OR gates. Let us go back to conclude to the 4-bit adder. It has been defined as an hierarchical structure, that is to say that the 4-bit adder is decomposed into 4 1-bit adder, so that it remains to synthesize the 1-bit adder. Here is the truth table that defines the function generated by the 1-bit adder. Observe that both C0 and Z have 4 minterms. C0 is equal to not X times Y times Ci, correspond to this row, plus X not Y Ci plus X Y not Ci plus X Y Ci. But you can simplify this expression. For example, not X Y Ci plus X Y Ci is the same as X plus X Y Ci, that is to say Y Ci. And you can do the same with the other terms. Don't forget that as the sum operation is idempotent, you can add X, Y, Ci as many times as you want, so that finally the simplified expression is Y Ci plus X Ci plus X Y. Then you can do the same for the Z function. In this case, there are no simplification. Finally, you get those relations, and from those relations you can deduce the following circuit. This circuit implements a 1-bit adder, and the 4-bit adder, this could be the first hierarchical level, and this is the second hierarchical level. Summary of this lesson: we have seen what a Boolean algebra is, how it can be defined, and which are the postulates and some of the main properties. We have seen that Boolean functions can be represented by tables. We introduced the concept of minterm and of canonical sum of product expression. Finally, we have seen how a circuit can be generated from a functional description. From the functional description, we deduced a table. From the table, a Boolean expression, and from the Boolean expressions, a circuit.